Hello everyone, hope you all doing well. My name is Panda, and today we're kicking off a brand new playlist called Machine Learning Design Patterns. Now the name isn't just catchy, it's actually the title of the book we'll be diving into. Machine Learning Design Patterns by Valipa Lakshmanan, Sarah Robinson, and Michael Munn. And I hope I got those names right. If not, my apologies. So why this playlist? Well, the goal is really to understand what design patterns are, figure out which ones are crucial for machine learning, and learn when, why, and how to use each one effectively. Another reason I wanted to make this series is that I'm not exactly a fan of reading, but I do want to dig into this material and make it accessible. So I thought, why not walk through the book on video? This way, I get to read and take notes, and you get the content without having to turn a single page. Alright, let's jump into chapter 1. The first chapter is a two-parter, where we are going to explore the history of design patterns and see why they matter for machine learning today. But before we dive into history, let's back up a bit. I keep saying design patterns, but what does that actually mean? At its core, a design pattern is a recurring problem with multiple solutions. Experts have analyzed these solutions over time and have pinpointed the most effective ones. And instead of reinventing the wheel every time someone hits that problem, we now have a name for the solution, along with its pros, cons, and guidelines on when to use it. So let's jump in and explore how design patterns shape the way we approach machine learning problems. Now that we have a handle on what design patterns are, let's go into their origins, which might surprise you. They didn't actually start in software. Design patterns first emerged in architecture. Architects, just like us in software, ran into certain design challenges again and again, and some solutions just worked better than others. The book highlights two interesting examples. The first is the light on two sides of every room pattern. Turns out, people generally prefer rooms with light coming in from two sides. Architects experimented with different layouts until they found this setup created the best ambience. They formalized it into a design pattern, light on two sides of every room. Now, while this pattern gives a guiding principle, it's still flexible. It doesn't tell architects where to place the windows, or even if the light source should be natural or artificial. They adapt it based on the specific project. But the concept remains the same. The main point here, design patterns provide a guiding framework that anyone can apply, but they leave room for customization based on the specific context. The second example is the 6-feet balcony pattern. This one suggests that if you're designing a balcony, it should ideally be at least 6 feet deep or multiples of 6. Why 6 feet? Because it's just enough room for 2 chairs and a small table. Go to 12 feet and now you have got both shaded and sunny areas. An 18-foot balcony gives even more flexibility. The idea is to use multiples of 6 to make the balcony a comfortable and functional space. Alright, that was a little taste of design patterns in architecture. Now let's move over to software design patterns. They first made an appearance in the software world in 1994, in a book that introduced 23 patterns for tackling common software engineering challenges. The book was titled Design Patterns: Elements of Reusable Object-Oriented Software. Since then, tons of other books have explored these patterns and even introduced new ones. Design patterns remains a key part of software development, and as many of you might know, they are popular interview topics for software engineers. Now let's continue our journey and see how these patterns apply to machine learning and why do we need them. As a machine learning engineer, we know that design patterns solve problems that pop up over and over again, and that some solutions just work better than others. But what are the patterns that are relevant to us specifically in machine learning? That's exactly what this chapter is all about. The book breaks it down by laying out the problem first, then exploring a few possible solutions before zeroing in on the best one, which is the pattern we're after. It's a systematic approach, where we will examine the advantages, disadvantages, and the context for each pattern to see why it is the best fit for the particular case. Each design pattern will be introduced in this way, but this chapter will take a moment to review key terminologies that will be used frequently. Understanding these terms is important to keep us on the same page as we go deeper. If you're familiar with these basics, feel free to move through them at your own pace. But having a clear understanding of these foundational concepts will make the journey smoother. The first concept the book dives into is machine learning itself. In machine learning, we typically deal with two main categories: supervised and unsupervised learning. Let's start with supervised. Here, you have features, which are characteristics of your data, along with labels, the target values or outcomes you're aiming to predict. Imagine we're predicting the price of a house. Our features could include the house size, balcony, proximity to shops, or even if it has a pool or not. The label in this case would be the price. For example, 180K. In supervised learning, our goal is to train models that can learn from these labeled examples to make future predictions. Common algorithms in supervised learning include linear regression, logistic regression, support vector machines, and decision trees. For more complex data, we have neural networks like CNNs and RNNs, for example. Now moving on to unsupervised learning, where things are a bit different because we don't have labeled outcomes. Imagine walking into a classroom full of students you know nothing about. Over time, you notice a natural grouping, a chatty corner in the back, diligent students up front, and some who seem glued to their phones. You didn't assign these labels, they just emerged. This ability to identify patterns or groupings in data without predefined labels is known as clustering. Telecom companies, for instance, might use clustering to categorize customers based on usage patterns, like frequent data users or long callers, and then create tailored plans. Popular clustering methods include k-means and dbScan. Another key task in unsupervised learning is dimensionality reduction, which is all about simplifying the data by reducing the number of features. For instance, when analyzing house prices, we might start with a lot of features: distance from the city, parking availability, neighborhood, and so on. But not every feature is essential. Dimensionality reductions help us trim down to what really matters, making analysis more manageable. Common methods for dimensionality reduction are PCA, which stands for Principal Component Analysis, and for visualization, TSNE. The third big unsupervised task is association rule learning. This is used to identify relationship between items. For example, if people typically buy eggs and then milk, a store could place these items close to each other for convenience. Alternatively, if they want to increase sales, they might place them far apart to encourage shoppers to walk through the store, potentially grabbing a few extra items along the way. With this intro to supervised and unsupervised learning in mind, let's move forward to a critical topic, which is the data itself, which is the fuel that powers our machine learning models. The book begins with how we split the data into three sets: training, validation, and test set. But why go through all this hustle? Why not just train on one big data set? Here's why. If you train on the entire set, you might see a sky-high accuracy, like 99%, and think you have built the perfect model. But as soon as you try it on new data, it could perform poorly. Why? It's because the model has overfitted. It has memorized the training data instead of learning the patterns that apply to the real-world scenarios. By using a separate test set, we keep an honest check on performance metrics, like accuracy or F1 score, for example. Let's say you achieve 80% accuracy initially. You then tweak the hyperparameters, maybe adjusting the learning rate or tree depth, to push it to 90%, maybe even 95%. But if you overtune, you might start fitting the validation data instead, leading to what we call overfitting on the validation dataset. That's why the test set is crucial. It's the final check, untouched by all our tinkerings, to give a true performance measure. So if our model shows 98% on training, 95% on validation, but 92% on the test data, 92% is what we report. Next up, let's get into the types of data. We have categorical and numerical data, each with further distinctions. Categorical data splits into ordinal and nominal. For example, clothing sizes, small, medium, or large, are ordinal because they have a ranked order. But colors, for example, like red, green, or blue, are nominal. No rank or hierarchy, just labels. Recognizing the difference is essential for how we treat data when building our models. Numerical data divides into discrete and continuous. Discrete data has fixed values, like the number of countries in the world. Continuous data, however, has a range, like house prices or temperature. Continuous data could have any decimal point values, like weight, for example, of 71.3 kilograms or 82.48. Discrete can also be decimal point values, but these values are limited and known, where it's any value between two numbers. Knowing if data is discrete or continuous lets us handle it correctly when training the model. With data types covered, we move on to preparing the data for our model, known as pre-processing. Models thrive on numbers, so we often need to transform categorical data into numerical form. Small equal 1, medium equal 2, large equal 3, for example. But for nominal data, say colors, assigning numbers directly could mislead the model. If red is 1 and green is 2, the model might assume green is greater than red, which is not the case. We will go over later how to properly encode nominal features to avoid this pitfall. The book also explains the difference between raw input data and features. Raw input is just the initial, untouched data we receive, but features are the refined, processed data that the model uses to learn. For instance, weight measurement between 70 to 80 kilograms becomes features after we normalize or scale them, transforming raw inputs into something the model can effectively use. After organizing and classifying our data, we need to validate its quality. This means checking stats like mean, standard deviation, variance, and interquartile range, which helps us understand its distribution and the relationship between values. Imagine most of your data represents affordable apartments, but then you test the model on luxury homes. It will likely struggle because it was trained mainly on lower prices. This kind of data imbalance can skew results. Data also shifts over time, which brings us to the concept of data drift. For example, gold prices from 4 years ago won't reflect today's reality. A model trained on outdated data will give us poor predictions, possibly leading to major issues. That's why we continuously monitor and update data to keep models relevant. Lastly, we must ensure the training data is accurate, with no duplicates, missing values, or errors. Even a tiny mistake, like an extra digit in someone's age, can throw the model off. The book gives an example where training data only covers weekdays, but the test data includes weekends. Such inconsistency leads to a poor performance since the model wasn't exposed to weekend data during training. When a model is trained on one thing but tested on something different, accuracy plummets. All these checks help us identify any potential issues that might arise. By reviewing and validating data, we can decide if it needs future adjustments or if we're ready to move forward. So now that we have classified, engineered, and prepared our data and validated its quality, it's finally time to move to the next big step, building the machine learning model. Machine learning has 3 key stages: training, evaluation, and serving. Training is like teaching the model from scratch. Evaluation is where you put it to the test, checking its predictions against the ground truth, like a test set. Serving is deploying the model in production so it's ready to make predictions in the real world. When a model is deployed, it can operate in 2 main ways. Online prediction, this is real time, like ChatGPT, you ask a questions and it replies instantly. Or batch prediction. Think of platforms like Spotify or Amazon. Spotify doesn't update your recommendations every time you switch a song. Instead, it refreshes every hour or 2. Amazon does something similar, updating product suggestions periodically, maybe every 2, 4, or even 10 hours, to save on computation cost. Batch predictions run in intervals, grouping requests to process them together. So online predictions runs continuously and in real time, while batch prediction can wait a bit and combine multiple requests before sending the outputs to save cost. Then there is streaming, a key concept for large-scale companies like Meta or Google that deal with massive continuous data flows. Think of posts, videos, or user interactions. Streaming allows them to process this incoming data in real time, making it ready for the next training cycle or for live predictions. This is crucial for managing data drift, as we discussed earlier. Without fresh data, a model trained on outdated information won't stay accurate. Real-time streaming feeds models with the latest updates so the predictions align with the current trends and conditions. Now let's dive into the data quality. because even the best algorithms need accurate, complete, and consistent data to learn properly. For data accuracy, we mentioned before both features and labels must be correct. If your data is mislabeled, even by a small amount, the model can become biased or inaccurate. Data imbalance is also a big issue here. Imagine a spam detection model where 90% of the data is non-spam. The model might just predict non-spam all the time and achieve high accuracy without actually learning. Using metrics like F1 can help identify when accuracy alone isn't telling the full story. Another factor is data duplication. If one class has many duplicates, the model might over-prioritize it, leading to a skewed understanding of the problem, rather than true learning. For data completeness, your data should cover all possible scenarios the model may encounter. For example, let's say you're building a model to identify cat breeds. If a user submits a dog picture, the model could wrongly classify it as a type of cat, because it's only trained on cat breeds. A practical solution is to add a non-cat class. Similarly, if your model only sees front-facing cats images, it may struggle with side or angle shots. Preparing data that cover these variations ensure the model performs well in real-world situations. Finally, data consistency, which means that data labeling is standardized to reduce bias. Labeling bias, for example, can creep in when different people interpret data differently. On Amazon, for example, a reviewer saying it's okay on a product might be rated 4 out of 5 by one of the labelers, and 2 out of 5 by another. To address this problem, we can use multiple labelers per data point and take the majority label to achieve as much consistency as possible. Now that our data is in top shape, let's dive into a big challenge that often surprises machine learning engineers: reproducibility. You know the drill. You're running experiment after experiment, tweaking configurations until you finally are done and ready to compare all these results. Then you find the results you're excited about. You rerun this experiment and you're ready to push this model into production, but then it falls flat. The results aren't matching what you achieved before. Sounds familiar? If not, don't worry. It's a common scenario that just about everyone faces at least once. The book explores the many reasons this might happen, starting with something as fundamental as data splitting. Even if you rerun the exact same experiment, small differences like change in the train test split can throw off results. To keep things consistent, use a specific seed to make sure your split don't vary from run to run. Beyond data splits, there's consistency in pre-processing and feature engineering steps. Any changes here can mess with the reproducibility, so stick to the same processes each time. Then we have hyperparameters. Yes, every little adjustment has to be kept the same, down to the exact learning rate. And let's not forget about libraries. Even small version changes in tools like NumPy or scikit-learn can make a difference. If you're training on GPUs, remember that differences in GPU models can also cause slight variations due to floating point precision differences. Basically, to keep results stable, you will want to control as many of these variables as possible. The book then circles back to data drift, which we briefly mentioned earlier. This type of drift can appear in two forms: concept drift and data drift, but we will dive in those distinctions in a later chapter. A good example here is predicting gold prices. If your model only sees data from several years, it won't be able to adapt to current trends in gold prices. Or take the storm data. The number of storms skyrocketed after 1990. If you're only training on data before this period, your model will give you predictions far from what's needed today. This is where streaming data or regular retraining steps are in to help these models keep up with these times. Now on to our last two major topics, which are scalability and multiple objectives. Scalability is a big deal because a model that performs well on a local machine might struggle at production scale. Serving predictions to millions of users brings a new level of complexity that needs to be planned and estimated. And then we have objectives. While you may be focused on minimizing the loss of the model, a product manager might be more interested in reducing faulty components reaching to the customers, aiming for higher recall. Balancing these competing objectives can be tricky, but it's crucial to align with everyone about the priorities. And that wraps up Chapter 1. We have covered the history of design patterns and why they are essential in machine learning, plus some common challenges that the upcoming patterns aim to solve. If you have got any questions, feel free to leave them in the comments below. And of course, your feedback is greatly appreciated. Until next time, see you in the next video inshallah. Bye bye.